Welcome everyone to Algebra 2, Section 7.7, Solving Exponential and Logarithmic Equations. So we're going to start with exponential equations. So hints that can help you to solve these. If you have some base to the power x and the same base to the power y, so a to the x and a to the y, then it's important to keep in mind that those exponents are going to equal each other. And we're actually going to see that on example 1, a, b, c, and d. So we would see 7 and 7 just raise the different powers of 3 and x. That's what that's talking about. The second tip is converting exponential. So that's where you see with exponents equations to logarithmic equations. And then the other one is to take the log of both sides, make the base the same as one of the other bases. We'll talk about that. And it's good to always check your solutions. So in example 1, like I was saying, this is going to be using that first hint where, hey, they're both the same base, a to the x and a to the y. So 7 to the third, 7 to the power of x. That just means 3 and x have to be the same. So 3 is x. On b, they're both 5 and 5, just different powers. So that means 3x plus 1 must be equal to 2x. The powers must be equal since they're both on a base of 5. So you just solve this equation. And I'd solve by subtracting 3x. So I'll have 1 equals negative x, divided by negative 1, and x equals negative 1. And if I plug that back in, I end up getting 5 to the negative second is equal to 5 to the negative second. And yeah, that's true. So I want you to try letter C and D on your own. On C, since their bases are both 4, 2x is equal to x minus 5. Solve this one by subtracting x, and you get x equals negative 5. Next one, since their bases are both 9, negative x plus 3 is equal to x squared minus 2x minus 3. This one's going to get a little more complex where we have to set it equal to 0 and factor. So I'm going to add x and subtract 3 from both sides and move these over. I'm going to put 0 on the right. So I get x squared minus x minus 6. And I do have 3 terms here, so I do need a factor. And so I make an x, negative 6 on top, negative 1 on bottom. 2 terms that multiply the top out of the bottom are going to be negative 3, positive 2. But I can use a shortcut because it's a 1x squared. So I do x minus 3 and x plus 2 equals 0. So solving these, or setting up the equations, gives me x minus 3 equals 0, x plus 2 equals 0, and thus my answers are x equals 3 and negative 2. And if we were to plug both those in, they both do in fact work. Alright, the second hint, changing the base. So, let's say on example 2a, you have 3 to the power of x is equal to 1/9 the power of x plus 3. So we can't do the same thing we did on example 1 because the bases are the same. Here, the base on the left is 3, base on the right is 1/9. But we can make 1/9 into 3. So we'll keep the left side the same, but 1/9 is really like 3 to the negative second, because the exponent of 2 would make it a 9, and the negative exponent would reciprocate it and send it to the bottom of the fraction. And so that is still being raised to the power of x plus 3. So what we can do from there is we can use our exponent properties and saying, hey, a power to a power, we multiply those powers together. So we have to distribute those exponents and say 3 to the negative 2x minus 6. Now, these bases are identical, both being 3. So we can set the exponents equal to each other and get x equals negative 2x minus 6. Once again, the reason we were able to do this, not at first, was because they weren't the same base, but we made them the same base because we said, hey, 3 to the negative second is the same thing as 1/9. And now since the bases are the same, because we made them be, we can do this. So move that up here, and from there, just rewrite it. Now I'm going to add 2x to both sides and get 3x equals negative 6. divide by 3, and x is -2. Letter B, we're going to do this very similar thing. I would encourage you to try this one on your own, or at least try to get as far as you can on your own. So the bases aren't the same, but we can make them the same. 49 is really like 7 squared. And so now we have a power to a power, so we multiply those with each other. So you do 7 to the power of x is equal to 7 to the power of 10x plus 36. So now since the bases are the same, we can set those exponents equal to each other and get x equals 10x plus 36. I'm going to subtract 10x from each side and get -9x equals 36. Move it up here and divide by -9 to get x equals -4. On letter C, you might notice, whoa, I don't think I can make 81 look like 1/3 well, and I don't think I can make 1/3 look like 81 very well. But we can make them both look like 3. So we're going to have to change both of the bases here, whereas on letter A and B, we only changed one of the bases. So let's get them both to 3. So 81 is like 3 to the 4th. And that'll be raised to 3 minus x power. And 1/3 is like 3 to the -1st power. So 5x minus 6. So now we take those exponents and multiply into them and get 3 to the 12th minus 4x. And over on the right, we get 3 to the -5x plus 6. So now since the bases are the same, we can set those exponents equal to each other and get 12 minus 4x is equal to -5x plus 6. From here, I'd solve by adding 4x, I'm going to add 5x to each side and get x on the left. I'm going to subtract 12 from each side and get -6. So I get x equals -6. On letter D, this time we only have to change one of the bases again. It's kind of nice. I would encourage you to try this one on your own. So 9 is really like 3 squared to the power of 2x is equal to 3 to the power of x minus 1. So here we don't have to necessarily distribute that because there's only one power there, 2x. So we're just going to multiply and get 3 to the power of 4x is equal to x minus 1. Well, 3 to the power of x minus 1. Now the bases are the same, so we can set the exponents equal to each other. 4x equals x minus 1. Subtract x from each side. 3x equals -1. Divide by 3. X equals -1/3. So the difference, once again, on example 2 versus example 1 is that we had to start changing the bases. Next, we're going to have a hint here that sometimes we're going to have to use logarithmic forms. And then we're going to have this base change rule, which we're going to use, where you say, hey, if you have log base b of x, we can turn these into log base 10s. And how you do that is you take log of x divided by log of b, and those would both be in base 10. So the reason this is important is because now you can use your calculator, because if you use the log button on your calculator, it assumes it's log base 10. So what you could do is on your calculator type log of x divided by log of b, and it'd be able to give you your answer. And we're actually going to use this here on examples 3a and b here, so we'll see it. So on example 3a, it says 5 to the power of 4x equals 29. It says isolate the power, then switch to logarithmic form. It's actually already isolated as much as we can because 5 is the one being raised with the exponent. So we're going to switch the logarithm using the spiral thing, where we move the 29 this direction, the 4x this direction. So log base 5 of 29 is equal to 4 times x. So we're saying 5 to some power, 4 times some power, is equal to 29. Now we can use that change of base thing, where we said log base, in this case, b of x, in this case b is 5, and x is 29. So that means 29 will go on the top because x went on the top, and 5 will go on the bottom because b went on the bottom. So we'll have log of 29 over log of 5 equals 4x, and those now are both base 10, meaning we can use our calculator for it. Now, before we start getting a bunch of decimals going around though, I'm going to multiply by 1/4 to get my x by itself. You could divide by 4 and it's really the same thing. I'm just choosing to call it multiply by 1/4 to not make it a double-decker fraction on the left side. So type this all into your calculator, log of 29 divided by 4 times the log of 5, and you would get x to the nearest hundredth to be approximately 0.52. Once again, that's using our change of base formula that we just have up here. Letter B, this time we will have to isolate the logarithm because there's a 5 with it, the power thing being raised to a power, and a -3. So we'll first add 3, so get 5e to the x is equal to 20. Divide by 5. E to the power of x is equal to 4. So now we'll switch to the logarithms by doing that rotation thing. And so we'll get log base e of 4 is equal to x. And you might remember, wait a second, log base e, that is the natural log. And the reason why that is so handy is because we don't need to use our change of base this time. You could, and you'd still get the right answer. But instead, you have a natural log button on your calculator. So you can just type in natural log of 4, and I'll tell you, to the nearest hundredth, it's approximately 1.39. All right, now we're going to start solving logarithmic equations. So a few different here as well. So condense all logarithms. So if they're expanded, condense them down. We just practiced that last lesson. If you have two logs of the same base, so in this case log of 10, log base 10, log base 10, of two different things, x and y, then they're equal to each other. That's very similar to that first hint we did for those exponential ones where we just said, hey, both things were 7 to some power. Third thing is get the logarithm by itself, so isolate it. Sometimes changing ln, the natural log, to log base e can really help. And then it's important to check solutions because you cannot take the log of a negative number. Now, example 4, we're solving for x. Now, remember, hint, if all bases are the same, that's this one right here, then use the quote-unquote easy method where the things inside, the things we're taking the log of, are just equal to each other. And condense first if needed. So, on A, log of 2x minus 1 is equal to log of 3x minus 8. So those are the same power, or same base of 10, the invisible 10 you don't see. So we can just say 2x minus 1, what's inside what we're taking the log of, I should say, is equal to 3x minus 8. So now you subtract 2x from each side to get x, add 8 to each side to get, not 9, but 7. And if you were to plug 7 in, you get log of 13 on both sides. On example B, we have to condense first, as it says, because you have the natural log of x minus 2 plus the natural log of 2x minus 3 equals 2 times the natural log of x. So we have to condense those things. The first one on the left side is using the product rule, where you have addition was really multiplication condensed. So natural log of x minus 2, let me write it this way, times 2x minus 3. And remember, 2 times the natural log of x was really the natural log of x squared. So now, since these are all being have the same base of log of base e, we can set them equal to each other. So we have x minus 2 times 2x minus 3 equals x squared. Now, before we go further, or in order to go further, we really need to distribute or FOIL this out. So we'll get 2x squared minus 3x minus 4x plus 6 equals x squared. Combining like terms will give us 2x squared minus 7x plus 6 equals x squared. Now we're going to want to subtract 7 or x squared from each side so we get it equal to 0. That way we'll be able to factor. So we'll get x squared minus 7x plus 6 equals 0. So we go to factor so we can solve. 6 on top, negative 7 on bottom. And we get a negative 6 and a negative 1. We can use a shortcut, woohoo. So we get x minus 6 and x minus 1 equals 0. Setting up our equations and solving them gives us x equals 1 and x equals 6. Once again, it's important to check our answers because we can't take the log of a negative number. So if we check them in our very original one, we get the natural log of 1 minus 2 using x equals 1, and that's natural log of negative 1. Oop, we don't even need to bother checking the other two parts of it because that can't work because you can't take the log of a negative number, and that's taking the natural log of negative 1. So if we were to plug in 6, what would happen? Well, we take the natural log of 4, the natural log of 12 minus 3 is 9, and 2 times the natural log of 6. So all of those are perfectly fine there on that one. So x equals 6 is the only actual answer because 1 makes the first one part a negative. So that would not work. Example 5. So a hint, if bases are different, condense or simplify, and then switch to exponential form. So a moment ago we were switching to logarithmic form on example 3. Now we might have to switch back to exponential form. So on 5a, it's already condensed. There's nothing else that we could do there to condense it. So we do the spiral thing again in order to solve this. So boom, 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 boom. And remember, it had a secret base of 10. So it's 10 to the power of 4.2 is equal to x. So we take our calculator out and we say 10 to the power of 4.2. And we get x equals 15,848.93. Or I should say it really approximately that. And we'll do a very similar thing on b, but first we have to get the logarithm by itself. So it's important to keep in mind that this is not part of the logarithm here. And one way we can know is that 1, it's not in parentheses, and 2, it doesn't have another log in front of it. So we'll add 1 to both sides and get the natural log of x equals 4. Now we'll do that spiral thing. And remember, that was really log base e, so we'll have e to the power of 4 is equal to x. And e is the button on the calculator you can use. So if you type in e to the power of 4 on your calculator, it'll give you that x is approximately 54.6. I rounded the nearest tenth that time. I should note, on a test, if I'm asking you to round, I'll say how much to round to. That way you know. Letter C. This time, we still need to get the log by itself by getting rid of that 4. So we'll have 5 times the natural log of 7x is equal to 15. Then divide by 5 and get natural log of 7x equals 3. Next, we want to do the spiral thing again here. So remember, there's a base of e when it's natural log, so e to the power of 3 is equal to 7 times x. So not only will we have to take e to the power of 3, we'll also have to divide by 7. So in your calculator, you can type all of that in at the same time. So e cubed divided by 7 gives you approximately 2.87 to the nearest hundredth. Then on letter D, this time we'll actually want to condense it first, because you have two logarithms on the same side that have the same base. And since they're adding, that means they were really multiplying when they were condensed. So we'd have log base 3 of 5x minus 12 times x equals 2. So multiplying those together gives us log base 3 of 5x squared minus 12x equals 2. So now we'll do a spiral with all of that. So 3 to the power of 2 is equal to 5x squared minus 12x. That tells us that 9 is equal to 5x squared minus 12x. This time we want to subtract the 9 and start factoring again. So I'm going to make it equal to 0 on the right. So I'm going to do 5x squared minus 12x minus 9 equals 0. Ooh, I'm going to make my x, and I'm going to put my result of the x up here. So 5 times negative 9 is negative 45, negative 12 on the bottom, negative 15, positive 3 do the trick. Cannot use my shortcut, so 5x squared minus 15x plus 3x minus 9 equals 0. Group the first two, group the last two. First two, 5x is what it has in common, and we're left with x minus 5. X minus 3, let's try that again. Second two, positive 3, and we're left with x minus 3. Now those are the same, and you're left with 5x plus 3 equals 0. Set those equations equal to 0, and solving them gives you x equals 3 as well as negative 3/5. Whew. We'd want to check our answer, of course, and you might notice as you check 3, you get 3 times 5 is 15, 15 minus 12 is 3, that one's fine, and 3, that one's fine. But negative 3/5, if we plug it in here, we end up getting a negative 3 minus 12. That won't be okay, that's negative 15. And this would be negative 3 over 5. So you take the log of a negative number, cannot do that, so that one's not a real answer, but x equals 3 is a legitimate answer. That one is a bit bigger, and that was the first one we had to do that condensing part, where we had logs with the same bases on that side. So we condensed it in order to be able to continue on solving. Whereas examples A, B, and C, we didn't have to do that when we isolated it because there were no other logarithms. On to the next part. 4 times e to the negative 0.3x power minus 7 equals 13. So at 7, 4e to the negative 0.3x power is equal to 20. Divide by 4. E to the negative 0.3x is equal to 5. Now it's time to turn it into logarithmic form. And by doing our spiral. So log base e, aka natural log of 5, is equal to negative 0.3x. So if you were to divide both sides by negative 0.3x, or negative 0.3 I should say, and type in natural log of 5 is equal to negative 0.3, don't have to do the change of base because it's just a natural log, then we end up getting x to be approximately to 2 decimal places, negative 5.36. Number 2, we haven't seen one like this in a bit, but it's one of our easier ones actually because they're both log base 7 on both sides. So you just take 5x equals 3x plus 15, where we're taking the logs of are equal to each other. Subtract 3x from each side to get 2x equals 12. Dividing by 2 gives us x equals 6. To be not 6. Let me try that again. I wrote, for some reason, and you probably caught it right away, 12. When it wasn't 12, it was, silly Mr. Kossel, 15. So, I wrote 12 again. 15 divided by 2 is either 15 over 2 or 7.5. Do I care how you write your answer? Not one bit. Next one, in order to get the log by itself, we'll divide by 6. Log base 2 of x is equal to 5. Then use our spiral. So we get 2 to the power of 5 is equal to x. 2 to the power of 5, that's 32. 32 is x. 4, we don't have logarithms this time, we just have exponents, or exponential form. We have 4 to a power and 2 to a power. Well, a reminder that we can change what 4 looks like. We can change 4 to being 2 squared. And now it's to the power of 5x plus 3 is equal to 2 to the power of 4x plus 12. So we can multiply the power to the powers and get 2 to the power of 10x plus 6 is equal to 2 to the power of 4x plus 12. Now, since the bases are the same, we can set those powers equal to each other and get 10x plus 6, excuse me, I almost said minus 6, is equal to 4x plus 12. Subtracting 4x from each side gives us 6x. Subtracting 6 from each side gives us 6. Dividing by 6 gives us x equals 1. All right, something new here is called the compound interest formula. This will be given to you on a test, just so you know. You will not need to memorize. A is equal to P times the parentheses of 1 plus R over N to the power of N times T. Whoa, that's a lot. So this is for compound interest, which you can have in different savings accounts, investment accounts, or on credit card bills as well. Are a bunch of different financial uses of this. So A is the amount, P is the principal, so the starting deposit of money, R is the rate of interest you earn, and it has to be in decimal form, N is the number of times per year interest is compounded, so typically it's not compounded continuously, like all the time, it's just compounded like once every few months or something like that. And T is after how many years are we trying to find the amount. So 6. You deposit $1,000 into an account that pays 7% annual interest compounded semi-annually. How long will it take for the balance to reach $1,500? So deposit $1,000. That's the principal. Pay 7% annual interest. So the rate, 7%, is 0.07 decimal. Move the decimal over twice, essentially. Compounded how often? So N, semi-annually, it's compounded 2 times per year. How long will it take to reach 1,500? That's the amount you want it to reach. And what we're looking for is how long. So time, we don't know. So now we take all of those things, we plug them into this equation, and we're going to solve for what we don't know. So we know A, we know P, 1 is just given, we know R, we know N, we know N again, but we don't know T. So we're solving for T here. So in order to solve for T, I'm first going to divide by 1,000 to try and get this and this part as much by itself as possible. Just like we were trying to get exponents by itself before, just a little more complex. Divide by 1,000, slash off those zeros, and I really get 3 over 2 is equal to 1 plus 0.07 over 2 to the power of 2t. So now we're going to do that same spiral method that we were doing a moment ago and turn it into a logarithm. So, but just keep in mind, we typically did it when it was, this part was on the left-hand side. So we'll really put it on the right-hand side here. 1 plus 0.07 over 2 to the power of 2t is equal to 3 over 2. That might help some of us there if we put it that direction. So now as we do our spiral, we can say, okay, we're going to spiral this and that. So we have log, and all of that is our base. So our base is 1 plus 0.07 divided by 2 of 3 over 2 is equal to 2t. Now, that's helpful for us for one basic reason, is that we can actually find this decimal, 1 plus 0.07 divided by 2. So if we take 0.07 divided by 2 and add 1 to it, we end up getting log base about 1.035, or exactly 1.035, of 3 halves is equal to 2t. So from there, we can use our change of base formula, which, reminder, change of base is saying log base b of x is really log base x divided by log base, or log of x, not log base x, divided by log of b. So we'd have log of 3 halves, aka 1.5, to make our lives a little easier, divided by, I should put the log part on top there, divided by log of 1.035, and that'll equal 2t. So this is very similar to an example we had earlier in the lesson where, let me see if I can find the exact number for it, where it was example 3a, by the way, so you can refer back to example 3a to see one similar, just slightly less complex. To get rid of the 2 with a t, we'll multiply by 1/2, aka divide by 2. So if you type all this in your calculator, it'll do the work for you, thankfully, and time ends up being approximately 5.893 years. Now, it didn't tell us to round to the nearest years, so we'll just leave it at that. So once again, we took what we knew from the formula. So we said, okay, we know P, R, N, and A. We don't know T, so we solved for T. And how we did that was getting the exponent part, the power by itself, then converting to a logarithm, then doing a change of base so we could type it in our calculator, and dividing by 2, aka multiplying by 1/2. All right, just a couple more examples here. If you have compound interest compounded continually, won't always happen. You have a formula A is equal to P times E to the RT. And where A, P, R, and T all mean the same thing. A still means the amount. P still means the principal. R still means the rate of interest, so the rate. And T is time in years. And how would you know which formula to use? It'll say compounded continuously or compounded like semi-annually. So on the last problem it said semi-annually, which is how you know it's not continuous. So example 1 here, number of camera phones shipped globally can be modeled by the function y is equal to 1.28 e to the power of 1.31x, where x is the number of years since 97, y is the number of camera phones shipped in millions. How many camera phones were shipped in 2002? So this we're not having to set up the equation, it already gives it to us. Y equals 1.28e to the power of 1.31x. And it says how many camera phones were shipped in 2002. So we need to solve for y, which is the amount, by plugging in x for the time. So how many years has it been since 97? If it's 2002, it has been 5 years. So y equals 1.28e to the 1.31 times 5. And this actually, you could just type all in your calculator right now. 1.28 times e and put it to that exponent. And it would end up telling you that y is the nearest million, about 874 million camera phones. And since y was already by itself, we could just type it into our calculator and say, yep, we're done with that problem. That's cool. Not every problem might be like that, but this one was. Some of them we're going to have to solve more like we did on the last one, by dividing and then converting to a logarithm and whatnot. Example 2, deposit $800 in an account, pays 2.65 annual interest, compounded continuously. So like I said, it'll say how often it's compounded. And what is the balance after 12.5 years? So amount, we don't know how much they're going to have after that much time, but we know we deposited 800. We know the rate is 0.0265, and the time is 12.5 years. So we plug those things in, and we get A is equal to 800 times e to the 0.0265 times 12.5. And once again, since we're solving for the part that's already by itself, we can plug all of this into our calculator and let it do the work for us and get the amount to be, to the nearest cent, approximately $1,114.17. So this person got a free $314.17 by letting their money sit in this account. That is all for section 7 and for chapter 7.